Okay. So today we will start solving some special model cases. So far what we did was basically two modules. In the first module, we showed what quantum behavior is and why we needed quantum description to explain some experimental observations. In the second module, you learned the language of quantum mechanics. So how you talk about the probabilistic picture of quantum particles, the wave function, and the postulates of quantum mechanics, which tell you how a wave function can represent a particle, how you can deal with it, the algebra that is that you need to know in order to be able to handle a probabilistic picture. Now we will use this algebra in certain model systems. So we will see the applications. We'll start out with the simplest models so that we can have simple solutions which we can understand. But eventually, what you learn here becomes useful only in more complicated situations where you need a computer to solve the Schrodinger equation for you. So what we'll basically do is we'll solve the time-independent Schrodinger equation for various model systems. We'll do particle in a one-dimensional box, two-dimension, three-dimension, then harmonic oscillator. Also, I'll talk a little bit about the free particle, and finally, we'll finish with the hydrogen atom. That will be the end of your syllabus. And in every model, we will learn different aspects of quantum mechanics, or more accurately, different techniques that are used to solve the Schrodinger equation. And what you will hopefully realize is that every problem requires a very unique method of solution. So if you know how to solve a particle in a 1D box, it might help you do maybe 2D or 3D at most, but along with some additional considerations, but it will not help you solve the harmonic oscillator or the hydrogen atom. So every problem has a unique approach. So that is a little bit special in quantum mechanics. Okay. So let's start first with the particle in a 1D box. Okay. So what do I mean by a particle in a 1D box? It means that I have a particle which is constrained to move in along a line between 0 and some length a. So I have a box of length a, let's say in the x direction, and I have and the particle cannot move beyond a. Why? Because there is a infinite potential wall on at 0 and at a, and also beyond it. So how do I mathematically say this? So I say that Vx is equal to 0 if x lies between 0 and a, and is equal to infinity otherwise. So basically then this particle that I am talking about is constrained to move only on this line between 0 and a. Now when something cannot exist beyond a point, then its wave function can also not exist beyond that point, because the probability of finding it before 0, so over here or over here, is 0. So these are called the boundary conditions. So for this problem, the boundary conditions are that psi x is equal to 0 for x less equal to 0 and x greater equal to a. And what about the Hamiltonian for this system? So this is a particle which is moving basically. So it has a kinetic energy and it has a applied potential to it. So this is the the kinetic energy operator, and this is the potential which is applied to it. Okay. Now, since the wave function does not exist beyond 0 and a, we can forget about that part, and we will solve the Schrodinger equation h psi x, let's say, equal to e psi x for x lying between 0 and a. And if that is the case, then I have said that v is equal to 0. So then my Hamiltonian is simply T. So what is the kinetic energy operator? Now this is basically minus h cross square by 2m del square del x square. This is the kinetic energy operator. So this comes from basically p square by 2m. Now, if I use the Schrodinger equation, we end up basically with a differential equation which needs to be solved. So I shift the constants to the right and I get minus 2m by h cross 2m e. Okay. Now I say that E must be positive. Now why do I say that? So firstly, intuitively, since the energy is only the kinetic energy, you would expect that it would always be positive. But there's also a way of thinking about it mathematically. That is, there is a theorem which says that the energy of a particle must always be greater than the minimum potential that is applied to it for all normalizable solutions to the time independent Schrodinger equation.
Ma'am, can we repeat the theorem once? Energy of the particle should be always greater than the potential applied to it.
Always greater than the minimum potential that it is subject to for all normalizable solutions to the time independent Schrodinger equation. So I'm not going into any sort of mathematical proof. It's kind of obvious if you just draw a simple diagram. So I have psi x and I have x. Okay. Now, if del square psi del, okay, 1 second. Sorry. So let's say E is negative, okay? So this is if E is negative, then the second derivative of psi is positive, okay? Which means that psi can either look like this or it can look like this. Okay. So if the second derivative is positive, so it will look right. You accept that it will look it will always slope in the either all upwards or all downwards. Now, if that is the case, then as
This
x
is only for this potential, right?
it is so here the potential is basically 0. So which is why this is the 0 line. Yes. So if b is 0, then and del d squared dx squared is positive, then psi can look either like this or like this. And in both cases, if x tends to 0, then psi x tends to infinity. And if x tends to infinity, psi x also tends to infinity. Now, such a situation can never give me a normalized wave function. For psi x to be normalizable, it should typically decay in the extremities, which means either as x tends to infinity, psi x should tend to 0, or in our particular case, it also means if x tends to 0, psi x should also tend to 0. This is for our particular problem. This can, in a different problem, this might translate to x tends to minus infinity, then psi x tends to 0. I mean, this depends, because here we have said 0 and a. That is why the limits here are x tends to 0, psi x tends to 0. But if you had something, centered at 0 and it would go in both directions, then the two boundaries would be x tending to infinity and x tending to minus infinity. And there, the wave functions should decay. And unless there is this decay, the wave function cannot be normalized, because normalized means that you should have a area of 1 under this curve, roughly speaking. So then, so that's why here, for a normalizable solution, E cannot be negative. Okay. So E must be positive. And if E is positive, then of course, this whole quantity is also positive. And I can write this as k square. So let's write as del square del x square C is equal to minus k square psi, which ensures that this is a positive quantity. Okay. Now this is a standard form of differential equation. So this looks like the differential equation for a classical harmonic oscillator. And we know the solution to that as psi x is equal to a sine kx plus b cos kx, where k is equal to root of 2me by h cos. So if you are not familiar with this solution, then then you can consider it like this. If I took a function which is just a sine x and I took two derivatives, I would end up with minus k square sine kx, right? So this first part is satisfies the equation. Similarly, this second part, if you take a double derivative, that will also give you minus k square psi. So you will get, you can at least verify that a sine kx and b cos kx, they are independently satisfying this differential equation. And if you have multiple solutions to a differential equation, then you can take a linear combination of them, and that will also be a solution to this differential equation. So you can write it as the solution as a sine kx plus b cos kx. So this is a solution to the differential equation. So you can think of it like that as well. Then, but now we have introduced two arbitrary factors a and b, and these need to be found out. So to find a and b, we apply boundary conditions, because we do know something more about the wave function. So we can obtain a and b. So the first thing is that psi of 0 is 0. So that tells me that b is equal to 0. Right? So I put x equal to 0 and I get a sine 0, that's 0, plus b cos 0, that's just b, is equal to 0. Fine. Then the next boundary condition I have is psi of a is equal to 0. And when I use that, I get a sine ka plus b cos ka is equal to 0, which means a sine ka. So I know that b is equal to 0, so that is removed. A sine ka is equal to 0. And then that implies that sine ka, and so a is certainly not 0, because if capital A was 0, then my wave function would be 0 everywhere. So assuming a not equal to 0, sine ka is equal to 0, which means it is equal to sine of n pi, where n is equal to 0 plus minus 1 plus minus 2, etc. Okay, which means ka is equal to n pi. Fine. Now, so what has happened? We were trying to find out a, but instead we end up with a equation for k, right? So at least now we found out some condition on k. So now we have a condition which k must satisfy, and this is actually a very beautiful fact, because it tells you that only certain values of k are allowed for you to have a solution to the differential equation. And this is the source of the quantization of the energy, because remember, k was equal to root of 2me by h cross. So if I say that k can only have certain values, it means that E can also only have certain values. So this is a very beautiful result that comes out automatically from the boundary condition on psi. But let's see, before that, what more we can say about k. So if n is 0, then k is 0, and that would mean that the wave function again disappears. Okay, so n equal to 0 is not allowed because if n equal to 0, psi x equal to 0 everywhere. My handwriting is really bad. Okay. Everywhere. Which means that there is no wave function, and that cannot be allowed. So n equal to 0 is not allowed. Also, if I consider the solution for n equal to 1 and n equal to minus 1, they are only multiples of each other. They only differ by in a sign. So they're basically the same wave function. Okay, and that sign can be absorbed into capital A, for instance, if you want. So the second point is that n equal to so let's say n equal to c and n equal to minus c are basically the same psi. Therefore, it is enough to take n equal to 1, 2, 3. So 0 is excluded, and we also exclude the negative ones because they're repeats. So now the next step now remains to find out A. So let's see how to find out A. Now for this we have to use something else. We have to use the fact that psi is normalized. And then we apply the normalization condition, which is integration from minus infinity to plus infinity of psi star psi is equal to 1. Now in our case, the problem is such that this integration will reduce to 0 to a, 0. And psi star is simply mod a square. So remember, we have not said if a is real or a is complex. So it can be anything. So I have to write mod a square and then sine square kx dx is equal to 1. And you can solve this in between yourself. It's not so difficult. And you end up with mod a square a by 2 minus mod a square by 2 1 by 2k sine 2kx. A is equal to 1. Now if you put x equal to a, then this will become, and then k equal to n pi, then you'll have this as 2n pi a. So this will always be 0. And you get mod a square equal to 2 by a, which means a is equal to. So you see, this is, I can take the real one. So I can take, so a turns out to be real. That is what I want to say. So a turns out to be real, and I get plus minus root of 2 by a. Again, since the sign of the wave function is not important, we can just select sine of psi not important. Therefore, we take a equal to root 2 by a. So the sine of psi is not important here because the physically relevant quantity is psi squared. So whatever the sign you take of the constant, they will eventually cancel. So we just stick to the positive one. You could have equally well taken the negative one, or you could have taken plus minus, it doesn't matter. Okay. So then what is the final solution that we get for psi? Therefore, finally, we have psi x equal to root of 2 by a sine kx, which is basically root of 2 by a sine n pi by a x, where 2n pi by a over here as well, where n is equal to 1, 2, 3, whatever. So this is my final wave function. And what tells me the energy? So we found a condition on k, which was that k is equal to root of 2me by h cross, which is equal to n pi. So if I square, then E is equal to n square h cross square. 1 minute. Square pi square by 2m. Okay, and I can cancel pi square from h cross square and end up with, so h cross is h by 2 pi. So I end up with n square h square by 8n. 8n, wait, one more. There should have been a n pi by a. Sorry. N a. 8n. So I get the energy and the wave function corresponding to each other. Okay.
These are just some of the possible solutions. It is not, I mean, the solution, right? I mean, these are just some of the possible solutions. Like,
this is, yes, just like a differential equation. In all cases, you, well, as long as you find some solutions, you are normally happy if they satisfy your problem. This is a set of, or a subset of the solutions, yes. But this this covers actually all the solutions finally, because you see, if n goes from 1 to 3 up to infinity, it covers, it is a complete set, so it covers all space. So let's say this is one of the families which satisfies this equation. So one other family is like, for example, e to the power I omega x. That is another equivalent family of solutions. But this covers all space. So you're not missing out on any function here.
okay.
Did you get my point? I mean, this is a
Yes.
whole set, yeah, covering infinite space. But you can have an alternative set if you want. Okay, so what is now remarkable about this? So now we have corresponding energies and wave functions, both of which depend on an integer n. So this integer n that sort of
Ma'am,
appears. Yeah.
it should be a square, right?
Yeah, 1 sine n pi by a. Yes, yes, yes. Thank you. Yes. I keep missing that a, so I hope I have corrected it everywhere. So k is equal to n pi by a. Yes. Yeah. So let me talk a little bit about this n. So this n is now a set of integers, and you have corresponding energies and wave functions, both of which depend on n. So if n is equal to 1, you have a energy given by h squared by 8ma squared, and a wave function given by root of 2 by a sine pi x by a. So you have pairs of energies and pairs of wave functions, and this gives you discrete energy levels and a wave function corresponding to this energy level. So automatically there is a quantization of energy. It crept in very innocuously. So it was just a boundary condition. The fact that psi a should be psi at small a, that should be 0 over here. Just this condition gave you a quantization. And this quantization appearance, you will see it appears in different ways. It's not always from a boundary condition. For different models, I mean. So when we do the harmonic oscillator, this n will come from a different source. When you do hydrogen atom, you will get more than one quantized quantum number. You will get the main quantum number n, then the angular quantum number L. Okay. So they come in from different sources, but they always come in. So this is really remarkable about about quantum mechanics when you're solving the Schrodinger equation. And sometimes you have the same model, same equation, but you solve it in two different techniques. We'll do that for the harmonic oscillator. So we'll do that in a direct differential equation way, and also in another operator kind of way. And in both, you will see that this source of the quantization is it's different in both cases, but it still creeps in, and the eventual answer is the same. So that is really remarkable. Okay, but this particle in the 1D box is of course a very simple one, and there is only one quantum number. And then we can draw the energy levels, and then I'll tell you a little more about the solutions. Let me first draw this thing. Draw the wave functions, because this is one of the few where you can actually draw it. So I have my box, and now this is the energy axis, and I have 0 and E. Okay. Now my first wave function is n equal to 1. So if n is equal to 1, then let me write it as maybe, okay, I can write this is En if you like. Then E1 is equal to h squared by 8m squared. And what does the wave function look like? The wave function is simply a sine function, which is 0 at x equal to 0. And it just goes, and x is scaled by pi by a, so it doesn't become 0 anywhere in the middle. It just looks like that. Okay. This is n equal to 1. Then let's look at n equal to 2. Then you have E2, which is 2 squared h squared by 8ma squared. And if n is equal to 2 over here, then when x is a by 2, you get a 0. So this will look more like this. Okay. Then for n equal to 3, I have e square is 8m a square. And here again I will have something that looks like so 1/3 of the way. Okay. So it will look like this. And one important thing to describe these wave functions is whether they are odd or even. So if we look at the point a by 2, then the lowest energy wave function is symmetric about a by 2. So we call that an even function. Then the next one is antisymmetric. So the two halves are of opposite side. So it's odd. Then the third one is again even, which means that the symmetries of the wave functions, they alternate between even and odd as you go up in energy. Okay. And the other thing to note is that the points
Ma'am,
at which the
excuse me, ma'am.
yeah.
Ma'am, could you please repeat that even
Yeah.
out once again?
Okay, so if the wave function is symmetric about the middle, here it is a by 2, then it is called an even function. And if it is antisymmetric, which means that one half is positive and the other is negative, then it is called odd. So if you reflect it about this middle point, the wave function will change sign. So that is odd. And then again, n equal to 3 is even. They're the same on both sides.
Okay, ma'am, got it.
Symmetric and antisymmetric. You can also say, yeah, you can also say symmetric and antisymmetric. This is just language. Okay. The other thing to note is the number of points in the range or the non-zero range of the wave function where it becomes zero. And these are called nodes. So we have so the ground state. So this is also called ground state. Okay. This would be first excited state. So this is just language. Okay. Second excited state. This is just okay. And then the ground state.
I have a question.
Yeah.
That I mean, Sourav sir had said that the wave function psi that we obtain, that must be continuous, and the first derivative of that must also be continuous. I mean, del psi by del x or something like that. So, here I am just wanted to ask that at the end points, the after that it is becoming zero, right? We claimed because of the infinite potential.
Yeah, I mean they are zero over here, and then they continue to be zero everywhere.
Yes. So isn't there a? I mean, that point isn't that a point of non-differentiability? I mean, that point is not. You cannot
But this
differentiate
wave
at that point,
function is
right?
not defined. This wave function, remember, we only solved in the range x greater than 0 and less than a. So x equal to 0 and x equal to a is excluded from the domain of the wave function.
Okay, but then but then the normalization condition. I mean, we took the integral from 0 to a because everywhere else it was 0, right? So
A wave function has to be normalized in the domain of that wave function. it's not. I mean, minus infinity to plus infinity is a guideline in a way. It's not. It's so if you. So, if, for example, if you have a wave function that you take from 0 to infinity, let's say, then you would normalize it in 0 to infinity. You would not normalize it from minus infinity to plus infinity.
Okay, but I mean, I thought that psi of x was was defined for all x, and we just have put this infinite potential, and that's why we should get it inside this box. Not that it is undefined outside. I mean, that is what I was thinking.
So outside, we are just saying psi is 0. I mean, we don't have an equation for the psi outside this potential here in this particular problem.
Okay.
Because you see, we didn't solve the Schrodinger equation for v equal to infinity. Because we can't do it.
Okay.
I mean, we don't. So the energy of the particle outside this box is basically infinity. If you want to think about it like that.
Okay.
So it doesn't really exist there. And actually, and the particle is also non-existent at 0 and at a. So it is always between 0 and a. So what happens at 0 and a is not of concern to us.
Okay, ma'am, got it.
So this idea of differentiability and continuity, that is as long as the wave function represents a particle. When there is no particle, there is no wave function, so it doesn't matter. Okay, is that okay?
Yes, ma'am.
Yeah. Okay. So then the other thing what I was saying is that So the points at which the wave function becomes 0 in the domain of the wave function. So between 0 and a. So for the ground state, there is no such point. For the first excited state, or n equal to 2, there is 1 point over here. And for n equal to 3, you have 2 points. So these are basically called nodes of the wave function. So a node of a wave function is a point where the probability of finding the particle is 0. This is again a very special thing for quantum mechanics, having nodes in a probability distribution. And for a particle in a one-dimensional box, the number of nodes is always equal to n minus 1. So for n equal to 2, you have 1 node. For n equal to 3, you have 2, and so on. And in order to find out the nodes, what you have to do is that you have to find out the point where the wave function is 0. So in our condition for nodes is n pi x by a should be equal to pi, 2 pi, 3 pi, etc. So these are the points where the wave function, that is the sign of this, becomes 0. And if you want to find out the condition for maxima or minima, then you have to take n pi x by a is equal to pi by 2, 3 pi by 2, 5 pi by 2, etc. Okay. So this is about the wave function. And now we'll talk a little bit more about, or the important points for particle in a 1D box. So what are our observations? So our observations from this exercise. 1. We get discrete energy levels. Then, which means that all energies are not possible. So this is definitely a quantum system. Then 2, there are infinitely many states. And like I've mentioned before, when we talk about states and we don't say state, what sort of state, they're basically energy eigenstates. Then the third thing that we saw was that they are alternately even and odd. Then the fourth thing that we saw is number of nodes is equal to n minus 1. And then the fifth thing, which I will show you now, is that the eigenstates are mutually orthogonal. So every eigenstate of energy that we've obtained, they are orthogonal. So let's look at the proof. It's simply a matter of working out an integral. So what we need to prove is that the integration of two eigenstates. So let's say one with quantum number m and another with quantum number n. When you integrate them from 0 to a, this will give you 0 for m not equal to n. So if you have two different eigenstates and you integrate them, then this is called an overlap integral. If you just take any two functions and you integrate their product over their full domain, that is called the overlap of two functions. This is a general mathematical quantity. And if two functions do not overlap, then they are said to be orthogonal. So this is what we need to show. Then it's just a matter of substituting the two functions. So integration psi m star psi n dx. So I've eliminated the for bracket x just for simplicity. So there was root of 2 by a, so root 2 by a into root 2 by a is 2 by a, and then integration from 0 to a of sine m pi x by a into sine n pi x by a integrated over dx. And this, remember, if I take the 2 inside, then 2 sine A sine B can be written as cos A minus B minus cos A plus B. So we'll use that trigonometry. We have 1 by A integration 0 to A cos m minus n pi x by A minus cos m plus n by x by A, okay, dx. Let's see, 1 by E, and if I integrate it, then I get A by m minus n pi, okay, and this becomes sine m minus n pi x by A, and minus A by m plus.
Ma'am, can you please
Yeah.
little bit go upward? Ma'am, can you please
More?
little bit go upward for a second? No, no, ma'am. It's okay. It's okay. Ma'am, I just missed this portion. Okay.
So I'm just doing basic trigonometric integration.
Yes, I'm done.
Yeah. Okay. So minus A by n sine m plus n by x by A. So this is what I get, and now I have to put the limits. I can also cancel this A here. So if I put x equal to so if I put x equal to A, basically the denominators cancel. So I get, and I can take, okay, pi common. Then I have 1 by m minus n sine m minus n pi. Okay. Then I have minus sine m plus n pi. Okay, 1 by m plus n. Okay. And if I put x equal to 0, they just become 0. I don't need to write that. And m minus n is also an integer, whether positive or negative, and m plus n is also an integer, whether positive or negative. So this is sine of some integral multiple of pi, so their values are also 0. So this is equal to 0. Okay, that's clear. So this is equal to 0. This is equal to 0. So which shows that if m not equal to n, then any two eigenstates for any value of m and n, they are orthogonal to each other. Similarly, if m equal to n, then what do you think will happen? You will simply get back the normalization condition. Okay, it will be the normalized. We have normalized it, so you should get 1 if m equal to n. You can verify that. Okay. The other thing which I said before is that the eigenstates form a complete set. What do you mean by a complete set? A complete set is a set of functions which covers all space. So you can represent any function using this set of functions as a basis. So if you haven't heard this language, maybe you can relate it to the Fourier expansion series. if that is more familiar to you. Then, like, you can use a Fourier basis set, which actually looks exactly like this. I mean, it, this is so a set of sine functions is forms a complete Fourier basis, for example. So in this case, we get a similar set of functions. So it is a complete basis, and you can represent any function as as a linear combination of this set of functions. So
Ma'am,
yeah.
ma'am, could you please repeat that from the the point six? Actually, I got disconnected that time.
Okay, so point six is basically that the set of solutions that you obtain for the particle in a 1D box, which is this set of functions, root of 2 by a sine n pi x by a, where n is equal to 1, 2, 3, up to whatever, infinity. This set of functions forms a complete basis, which means you can write any arbitrary function as a linear combination of these functions. So all points in infinite space are a part of the function space of this set of functions.
Okay, ma'am, got it. Thank you, ma'am.
Yes. Now I will not show the proof of this. It's a bit more involved than necessary. But the fact that you can do this is very important. Okay. Now the other thing is, what if?
Ma'am,
Yeah.
actually, even in the maths methods course or even in the sort of sir's part, I mean, this was again just mentioned. This was not proof. So, could you, in the when uploading the slides, could you attach?
Some proof of this?
Yes, yes, because
Okay, okay,
we are
okay.
hearing it again and again and again. But
Yeah,
just,
this is very important. You will use it very many times, both in physics as well as in chemistry. Okay, I will look at it. I'll send you some sort of proof. So the proof basically involves a lot of mathematical terms, so it becomes difficult for people from all backgrounds to understand it, which is why everyone avoids it. But if you want it, I can share it with you.
just as an extra reading.
Yeah, okay, okay, sure. Then the next point is we solved the time independent Schrodinger equation. Okay, but let's say we wanted to find the time dependent wave function for this problem. So if we wanted to see the wave function as it evolves in time, like I have mentioned before, which is also a very important thing, so even though eigenstates of the Hamiltonian are called stationary states, they are not in reality stationary. The particle is dynamic, and so is the wave function. Okay, and you know that when when you look at the solution for the time dependent Schrodinger equation, and you're talking about an eigenstate, you only get a phase attached to it. So if you remember that, then any stationary state is basically the time independent state multiplied by a phase factor. And it is called a phase factor because there is an imaginary I multiplied with it, which depends on the energy of that eigenstate. So this is the important part. So here, since we know En, we know psi x, the time dependent wave function is also known, okay, for the eigenstates. So this means that solution of the time dependent Schrodinger equation for the eigenstates is also known. But what if you don't have an eigenstate? If there is a non-stationary state, can we solve the time-dependent Schrodinger equation for this problem? So let's see. Now that we solved the time-independent solution, and we know that the eigenstates form a complete basis, I can expand any general non-stationary state, so a general state, as a linear combination of the eigenstates. So this is just a representation. My task is still not done. And I have e to the power minus I n t by h cross. Okay. So I'm using the time independent state multiplied by the phase factor now. So this whole thing is acting as the basis for expanding a general non-stationary state. And my task is to find out Cn. Okay. And in case of the time-dependent solution, you always need the starting function, because you need a function at t equal to 0, and then you find out the wave function as a function of time. Otherwise, it doesn't make any sense. Okay. So, knowing psi x0, which you can choose that to be an eigenstate if you want, which you already know. Then, so here, knowing psi x0, can we find the CNs? So I just said something that is, well, not quite correct. So I said you can choose psi x0 as an eigenstate, but if you want that your function is a non-stationary state, you can't do that, because if it was an eigenstate, then its time evolution would simply be this phase factor. You would not be able to go to a non-stationary state. Okay, because here you have to choose psi x0 as a non-stationary state, and only then you will have a time evolution which will be which will take you to other non-stationary states, if that is what you want. To do that, you have to basically then find a non-stationary psi x0 and then start with that. So how do you find out the starting function which is non-stationary? So psi x0 can again be written as a linear combination of the eigenstates. So this is at t equal to 0, so I don't need the phase factor here in the basis. And then we can project with psi m to find out the coefficient Cm, for example. So let's see. To find Cm, we project psi mx. So psi mx is another basis function. Okay. So then psi m psi is equal to sum of n equal to 1 to infinity Cn psi m psi n. And we proved that they were orthogonal. So I can write this as Cn delta mn, delta function. So which means it will give me Cn. Okay. So Cm will give me some value. So the left hand side I can open out as an integration. Sorry, psi m star dx. So I find out the overlap of my starting non-stationary state with each of the basis functions as they are called. So let me just write this. So I can say this is a basis function. This is a basis. This is a time dependent basis function, and this is a time independent basis. Okay. So we are finding out the overlap of every basis function with my starting function, and that is telling me the coefficient in the starting function. Okay. So we'll find out all the coefficients of the basis in this way, and from that, after that, you can start solving the time-dependent Schrodinger equation. So we will not go that far. I just wanted to tell you how the various time-dependent and time-independent basis functions can be generated from the solutions of the particle in a 1D problem. So that's about it for the one-dimensional box. So it is the simplest model which shows you all the essential components of the quantum mechanics of a single particle. Now, some additional interesting things happen when you go to 2D and then to 3D. So I have half an hour, so I'll finish the 2D today. So particle in a 2D box. So what is a 2D box? A 2D box is now some sort of rectangular box. Okay. And the particle is confined there. So it can move in x and it can move in x and y directions. So it can move inside this box, but otherwise it is there is an infinite potential in other places. So if I want to put it mathematically, then the potential is Vxy is equal to 0 for x lying between 0 and a, and y lying between 0 and b, and is equal to infinity otherwise, which means basically it is confined to an xy plane AB. Now, the Hamiltonian for this is again quite easy, in that it can just move in x and y direction. So it has kinetic energies in the two directions. So h psi equal to e psi. This is basically del square del x square psi plus del square del y square psi equal to e psi. And this is multiplied by minus h cross square by 2m, which means now del square psi del x square psi plus del square psi del y square is equal to minus 2me by h cross square psi.
Ma'am,
Yeah.
we only did the momentum operator for one dimensional case, which was minus I h cross del by del x. This was the momentum operator. So for the 2D case, I don't know how we can get. I mean, because we got the Hamiltonian from. I mean, that was the prescription to substitute operator for p and operator for x to get the operators, right? Any other general operator. So in this case, when it is 2D, can you explain how we can get the momentum operator?
Yeah, so basically the motion in the x and y direction, they are independent. So the momentum in the x direction gives you a certain kinetic energy. The momentum in the y direction gives you another kinetic energy, and the sum is the Hamiltonian. So they're independent.
Okay. So I mean, are you saying that if we don't write in the operator language, in just the, I mean, in classical language, that will be px square by 2m plus py square,
Py square by 2m, exactly.
and then we will substitute the operators for px and py
X
separately.
and py separately, yes.
Okay.
So here there is nothing that couples the two motions. It's independent. So that's why
Oh, okay.
you can just write it as a sum. If there is, for example, some potential, external potential which restricts something. So if you have maybe a particle which is moving in a circle or something, then because of an external potential, then you would no longer be able to write it so simply. Then you
Okay.
would have some coupling terms, but say some product of px and py. But if there is no external potential which restricts your motion in any way, then the motion in the x and y direction are independent.
Okay, ma'am. Thank you so much.
Okay, so we proceed in the same way. So again, the energy is positive, like because of the arguments given before. So I can write it as k squared psi, where k is then equal to root of 2 and e. Anyway, now we will do something special. So what is the special thing we will do? We will look for solutions of the form psi xy equal to x of x and y of y. So we're only going to look for solutions which are product separable. So this is again another terminology. So product separable. Now why we're doing this is because we're a little bit wise after the event. So if you have a sum of terms in the Hamiltonian which depend on different variables, then the solutions or the wave functions which are solutions to the Schrodinger equation, they appear in product form. So this is something we know from experience. And so I'm using it to show you the solution of the 2D problem in the simplest possible way. Okay. So this is of course not how people have done it initially. So they have struggled much more. But we will do it in the simplest possible way. which is we will look for solutions which are product separable. Okay, and that is because, like we were discussing, the x and y variables in the Hamiltonian, they are totally separate as a sum. We could not do this again if there was some coupling between them. Okay, so let's see. So now we have h psi xy equal to del square del x square xy plus del square del y square xy. Well, I shouldn't write h psi, but because that is a factor. But so, okay, I'll just write it at the end if you don't mind. Or okay, I'll write it here. Right. So this is equal to minus h cross y x double derivative plus x y double derivative. Okay. So then we can write so now I'm getting rid of the constant again. I hope that is not a problem. So we have y x double prime plus x y double prime is equal to minus k square x y. Then I divide throughout by x y. So y x double prime by x y plus x y double prime by x y to minus k square. Then x double prime by x plus y double prime by y is equal to minus k square. Okay. Then x double prime by x is equal to by y. Now something funny has happened. So we have a left hand side which only depends on x, and we have a right hand side which only depends on y. So how can we have a solution to a differential equation which looks like this? The only possibility is that this is now equal to some constant. So only possibility for solving this is that x double prime by x equal to constant and minus k square minus y double prime by y constant. Okay, and this constant I will write as minus lambda square in this form because this will let me solve this equation easily. And here lambda can be complex. So that covers anything that might, whatever the value of the constant may be. If I say that the value is minus lambda square and lambda can be complex, it can assume any value, positive or negative. Remember, k we had restricted to being, so k is only real because k square must be positive. If I let k be if I let k be complex, then there is no guarantee that k square is positive. So k can only be real. But here, this constant can be anything because we don't know what it is. But why we are writing it in minus lambda square form is because we want to use the solutions from the 1D problem. So then if I write it as minus lambda square, then this equation, let's say I call this 1 and 2, then from 1 x double prime is equal to minus lambda square x, which looks exactly like my 1D problem. So I immediately know the solution of xx, which is root of 2 by a, which is my boundary in the x direction, sine n pi x by a. Now since we have a 2D problem now, I'll subscript the n with x, indicating that nx is the quantum number for the x direction. Okay, and where this is basically lambda. Okay, let me just write one more step. Root of 2 by a sine lambda x, and that is equal to root of 2 by a sine nx by x by a. Okay. And okay, so but remember there's something else to think about over here. So the boundary conditions that we used to get all these factors here, they involved only the x variable. So our boundary conditions before, or the ones that have been used here, is x0 equal to 0 and xa equal to 0, right? But is that true? Because the boundary conditions for this 2D problem is that psi, so this is, so I'll just put it in a bracket to indicate that this is what has gone into this solution. But what are the boundary conditions for the 2D problem? It says that if x is equal to 0, then for all y, the function is 0. Also, if y is equal to 0, then for all x, this is 0. Right? Similarly, if psi is a, then for all, or x is a, sorry, if x is a, then for all y, this is 0. And if psi b, so this is my true boundary conditions for the 2D problem. But when we apply this product form now, so from here, this says that x0 into y is equal to 0. Okay. Let's call this A, B, C, and D. A, this is 0. Now since y is not equal to 0 for all y, then it would mean that the wave function in the y direction is simply disappearing, which cannot be. You get the reduced boundary condition that x is 0 equal to 0. Similarly, if I am looking at,
One question.
yeah,
Ma'am, why should we get root 2 by a multiplied by the x bar since we had gotten that from the normalization condition, which was for the entire, wave function, not just for. So, that condition should be for x. X and y both together. Why are we getting root 2 by a in the x part?
Yes, that is a very, very good question. But okay, so I'll do that. Just 1 minute. Let me just finish the C and I'll show you the normalization. Okay. So this is this, and from have uh, x a into y equal to 0, and again by the same logic x a equal to 0. So the boundary conditions here are fine. So let's see. So good question. What about normalization? So the normalization condition in this case is basically a double integral from 0 to b and 0 to a mod psi x y square dx dy, okay, equal to 1. Now, if I write the psi as separately, as product separable, then I get mod x square yes mod y square equal to 1. That can be separated as okay. So I have a normalization condition which is also kind of product separable. So if I choose, so I can choose that this is equal to 1 and the x part is separately equal to 1. And this would satisfy the normalization condition for the overall wave function.
Oh, okay, okay.
Okay, so this is a choice. Anyway, 1D, fine. So this is this. Now what remains is to solve for yy. Okay, I'll just do that. So let's now solve for yy. So my equation was minus k square minus y double prime y equal to minus lambda square. So I can just do that. Okay. And I get y double prime y is equal to lambda square minus k square. Okay. And that I can write as minus of k square minus lambda square and y double prime is equal to minus lambda square y. Okay. So now we have again got it into this classical harmonic oscillator form. So now I will again use the same solution, that y, or the same form of solution is equal to a sine then root of this quantity k square minus lambda square y. Okay. Now I will use the boundary conditions. That is yb equal to 0, which means a sine.
Ma'am, how do we know k square minus lambda square is greater than 0?
We don't.
Okay.
We don't, but it is only when the when k square minus lambda square will be greater than 0 that you will have a valid solution. So
Okay.
it's, yeah. This in brackets. Square b is equal to 0. So which means I can write this as sine ny y by ny equal to 0, 1, 2, blah blah blah. 0 plus minus 1 plus minus whatever. Then okay, I'll just remove a from here as well, because a is definitely not equal to 0. And then I get root over k square minus lambda square b equal to ny by, and then root over k square minus lambda square by b. Okay. Then again we discard ny equal to 0 and also all negative ny. Therefore, ny is equal to 1, 2, 3. Then yy is finally root of, okay, if we do the normalization condition, we will get root of 2 by b. You can verify that. I'm not doing this because we're almost out of time. So 2 by b sine ny by y by b. Okay. Therefore, psi xy is simply xx into yy, which is equal to root of 2 by a sine nx by x by a, root of 2 by b sine ny by y by b, okay, which is equal to 2 by root ab sine nx by x by a sine ny by y by b. Okay. So we got the wave function and then the energy. So energy so k square minus lambda square is equal to,
Mom, can you scroll up a little?
yeah,
Mom, a little more.
more. Is that okay? So to find the energy, basically we need to know k square. So we have a relation between the energy and k square. So we'll find out k square from this the y direction quantization condition, and then we will substitute. Yes. Have you finished? I'll send it to you anyway, so you can complete it later. No problem. So, okay. So k square. So remember, we knew that k square is equal to 2me by h cross square. So as soon as we know k square, we can find out e. And we'll find out k square from this relation, that k square minus y square is equal to ny square pi square by b square. That is this condition that we got over here. This one. This is this. And that tells you that k square is equal to plus, okay, remember lambda square? We also know what lambda square is. So we found out lambda square somewhere. Lambda square was related directly to nx squared. So that was nx square pi square by a square. And then, therefore, E is equal to h cross square by 2m. And then I can take pi square common. And I can write nx square by a square plus ny square by b square. Something I did wrong. Okay, no, fine. This is h cross square. So I can open out h cross square as h square by 2 pi. So I will get 4 pi square. So that's 8 pi square and pi square. And I can cancel pi square. So the final answer is E is equal to h square by 8m nx square by a square plus ny square by b square. Okay, so it's so the energy expression is kind of analogous to the 1D case as well.
Ma'am, didn't we get an expression of this form for counting the number of modes in that black body radiation case?
It was something similar, but I think we didn't have the squares over here, as far as I remember.
I think it's because like over there also we assumed the standing wave kind of patterns also. Same as here. So probably why we're getting similar things. It was very similar to this also. That's it.
It looked similar, yes, but this is an energy expression. That was
That was for frequency, ma'am. I think.
that was some yeah. That's also related to energy. Yes. Yeah, it's similar, but I wouldn't put too much into it. There, the principle was different. Yeah, but here, what you note now is that so you have what should I say? So you have now pairs of quantum numbers for every wave function. So you already have two. So in 1D case, you had one quantum number, and here you have two, nx and ny, which are independent in this particular case. But if the motion was coupled, they wouldn't be. So we'll finish here for now. So it was a long class today. But I want to finish the syllabus a little bit before. Maybe by end of October, I want to finish the syllabus. So you'll have more time to study. Okay, so yeah.
Actually, I wanted to say something that I mean, you have raised this objection to the TAs also, that many of the questions in the exam, while I mean, it was taught theoretically, like what is this supposed to be and something like that, but we were not the tutorial was not taken on how to do, for example, problems on operators or things like that. So we were seeing them for the first time in the exam. So it's my request that if some like problems
You
with
want some more tutorials? Yeah.
yes, yes. I mean, whatever is related to the uh, course that is, I mean, whatever is supposed to be asked in the exam, something like that, for those kinds of things.
Okay, we will try. Actually, we don't have that much time. This is a very big syllabus for a 2-point course. So we are kind of short of time always. I
We will finish early. That's why I was saying.
Yeah, so if okay, what I can do is I will finish early by end of October, and then in November we will try to accommodate as many tutorials as possible. Because actually, I will go on leave from beginning of November, so I will not be able to take classes. But I can set a problem sheet and get the TAs to solve them for you in November. I guess that should be kind of helpful. And in between, of course, we will have maybe one more quiz or something. So before that, I'll try to see if we can have a tutorial before the quiz.
Yes, ma'am. That was my request. That before a exam or a quiz, if it's possible to at least, I mean, to do problems on some kinds of related at least things. That was.
Yeah, so there will be one more assignment, one more quiz. So the assignment will come before, so you'll have some practice, and then maybe a tutorial, then a quiz, and some more tutorials before the exam.
Yes, ma'am.
We'll
Thank you.
try to do that. Okay. Okay. Thank you. So I will stop screen sharing, and I will try to sort out your mark C problem and ask and see what can be done. Okay. Thank you.